Log on, tune in, find out. Another good idea from Cambridge.
Science, Kyoto University. The title is on the blackboard. So, localization affine W-algebras.
Thank you very much. First of all, I'd like to thank organizers for the invitation and for organizing such a nice conference. So my talk will be based on the joint work with Toshiro Kuwabara and Fyodor Markov. So let me fix my notation. So G will be a finite dimensional simple. The algebra over C, and for some traditional reason I write F for an nilpotent element in G. And I take SL2 triple. Then from this data one can define double algebra V affine double algebra associated with G and this nilpotent element at level K. So K is a certain parameter. So Goodwin talked about finite double algebra, which is usual associative algebra. But affine double algebra is not a usual algebra, but it's a vertex algebra. So this is just this is a vector space, and for each element A in here, so infinitely many application is assigned for each element. Infinitely many multiplication is assigned for each element in this. And this operator subjected to certain relations such as Boucher's relation, which involves infinite sum. So it's quite a complicated object, but at the same time, so vertex algebra often can be considered as a quantization of some nice object. So it's often, not always, but quantization of the infinite jet scheme x infinity of affine Poisson variety X. So I put infinity to indicate this is a jet scheme of X. And all of vertex algebra in my appearing in my talk will be a quantization of a jet scheme. So I don't want to give I don't give the precise definition of double algebra because I don't want to start with the explaining the definition of vertex algebra. But instead I try to give you idea what it looks, what it is like by explaining what the corresponding associate graded are. So associate graded of a affine double algebra is the infinite jet scheme of the Srodoi slice, which appeared in the Godwin's talk. So this is a Srodoi slice. And it is known the Gelfand-Kirchhoff Poisson structure of G star restricts to the Poisson structure of the Srodoi slice. So this is for any k. So you can think affine double algebra as a one parameter quantization of infinite jet scheme of Srodoi slice. Or another thing is that the affine double algebra is related to the finite double algebra by Zoo's functor. So the Zoo's algebra of affine double algebra is isomorphic to the finite double algebra, which appeared in the Godwin's talk. So this is for any k. So I don't want to explain what Zoo's algebra are, but this means that the double algebra is a affine double algebra, certain affinization of a finite double algebra. In particular, there's a one-to-one correspondence between irreducible highest weight representations of affine double algebra and the irreducible finite dimensional simple irreducible finite dimensional module over finite double algebra. So by irreducible highest weight representation, I mean what VOA people call ordinary representation, which is a graded representation bounded from above. So you have a grading and there's a top part with respect to the grading. So the assignment, the correspondence given by sending a simple module to the top part of the simple module. So the Zoo's algebra acts on the top part of the highest weight representation. So it's kind of a zero mode algebra. And the inverse correspondence given by, so there's a certain induction functor from here to here. So we just take a certain induction and take a irreducible quotient. So this is so if in the if you consider the affine non-twisted affine Kac-Moody algebra associated with G, and if you fix level, then the parameterization of irreducible highest weight representation is the same as the parameterization of irreducible highest representation of G, and the correspondence is exactly given by this. So it's really affinization of a finite double algebra. And unfortunately, so Goodwin explained that in some nice cases this has a presentation, but unfortunately for a fine case it's so complicated and no presentation is known, except for minimal nilpotent case. So this makes things quite difficult, but at least so in some years ago we have proved that the character formula of irreducible highest weight representation of G hat. So at least for type. So this is for type A. So at least for type A case, character formula of G hat at level K gives character formula of corresponding double algebra for any K and for any F. More precisely, there is an exact functor from the suitable parabolic category O of G hat to the category of modulo over double algebra, which sends a simple modulo to 0 over simple, and sends the standard modulo to standard modulo, and any simple modulo appear in this way. And of course, this is an analog of result of Brandon and Kuleshev, who determine the character of finite reducible finite dimensional representation of finite double algebra of type A. And my result heavily depends on the result. For example, the classification is the same as a finite double algebra, so we need result from finite double algebra. So anyway, so the double algebra has parameter k, and if k is not critical, where H is the dual Coxeter number, then it is known that the Kashiwara Tanisaki, that the character of G hat is given by the Kazan-Lustig polynomial. So the character here is also given by a Kazan-Lustig polynomial associated.
Where is the F on it? Where is the nilpotent on the left-hand side of
No, there's no F here. So the functor changes according to F. And if K is minus H, then the Fagin Frenkel conjecture says character formula here should be described in terms of a Lustig periodic polynomial. So this character formula here should also given in terms of periodic polynomial. So this makes me think that the double algebra of this special value of the critical level should be interesting. So today, let me put K to be critical level, which is minus of a dual Coxeter number, and let me look at the affine double algebra as a critical level. So first, let me recall some result in the case of f equals to 0. So in this case, finite double algebra is just an enveloping algebra of G. So accordingly, affine double algebra is essentially corresponding Kac-Moody algebra. But we are talking about the vertex algebra, so the corresponding object is vertex algebra associated with G. So this is often called affine vertex algebra associated with G at K. But the representation of this vertex algebra is essentially the same as a representation of G hat at the critical level. It's a smooth model, but it doesn't matter if as long as we are looking at highest weight representation. So a smooth representation of G hat at K. And so this is somewhat the reputation, but the associated gradient of this affine vertex algebra is, of course, the jet scheme of G star, which is identified with the symmetric algebra of G negative. So I considered this as a function on G star infinity by the residue pairing. And so this also reputation, but of course the Zoo's algebra of this vertex algebra is isomorphic to the enveloping algebra of G. So this is not the special feature of the critical level, but there's one special thing happening at the critical level. Namely, there's a big center in this affine vertex algebra, which is called Feigen-Frenkel center. So this is a center of the affine vertex algebra. So by By a center of a vertex algebra, I mean the following. Oops. So if V is a vertex algebra, so there's infinitely many operations, and the center of a vertex algebra is a space spanned by the element whose multiplication commutes with any other multiplication. And it's easy to see this forms a commutative vertex subalgebra of V itself. And by Boucher's, a commutative vertex subalgebra, a commutative algebra is the same as a differential algebra. Which I mean C algebra, a commutative C algebra with a derivation. So, for example, functions on affine, the jet scheme of affine variety is a differential algebra. So this explains why jet schemes are pairing. Anyway, so this is Feygin-Fraenkel center, and the Feygin-Fraenkel center, associate gradient of Feygin-Fraenkel center is again a jet scheme of the adjoint quotient, or invariant in the invariant ring here. And also Zoo's algebra of Feygin-Fraenkel center is isomorphic to the center, usual center of the enveloping algebra. So Feygin-Fraenkel center is a kind of affinization of the usual center of enveloping algebra. And these are a beautiful analogy due to Feygin and Fraenkel. Okay. Goodwin talked about the center of finite double algebra. So I now want to describe the center of affine double algebra. So the center, there's a natural, the center of double algebra is trivial unless at the critical level. So it makes sense only to consider when it's a critical level. And there's a natural map from the center of the from Feygin-Fraenkel center, just like in the finite dimensional setting. And the statement is this is again isomorphism. And moreover, so this is a commutative vertex subalgebra. So in particular, it's just a usual ring structure. And the critical double algebra is free over Feygin-Fraenkel center. And of course, this is analog of result of Prime and Ginzburg, which this was explained in the previous lecture. But so the center of finite double algebra is isomorphic to the center of the universal identical algebra. But there's another feature which does not exist in the finite dimensional setting. So this is center. So you can consider quotient vertex algebra by dividing the ideal generated by the positive part of the Feygin-Fraenkel center. And I denote by this W0 GF. And the statement that this is simple. This is a simple vertex algebra, which means that the it's a irreducible modulo over affine W-algebra. To prove the first statement, it's easy to show that this maps injectively to the center of affine W-algebra by the functoriality of the jet scheme. The difficult part is to show the surjectivity, but this is done by showing the second statement. So if this is already simple, then the map must be surjection. So you have a nice analogy here. Before going further, I should make some comments. So Goodwin explains the constant result. So there is an analog of constant result by Feygin-Fraenkel. So if you take principal nilpotent element, then the W-algebra itself is commutative. And this is isomorphic to the Feygin-Fraenkel center. So this is an analog of constant result. Also, if you take f equals to 0, then the simplicity of the quotient by the positive part of the center is a result by Feygin, Fraenkel and Gasguri. So this is Fraenkel and Gasguri. And my proof heavily depends on this result.
Sorry, I didn't understand. Can you say again what is W sub 0 to
It's so this forms ideal in this vertex algebra. So you define quotient vertex algebra.
Oh, that's the definition.
This is the thing.
Is it normal?
I'm going to explain. Okay, so now let S to be intersection of this Rodriguez slice with the nilpotent cone of G. Then this result from this result it follows that the associated gradient of this simple vertex algebra is isomorphic to the function on the infinite scheme of S. So this should answer your question. And also those algebra of this simple double algebra is isomorphic to the quotient of a finite double algebra by the positive part of the center. So you have again nice analogy here.
But what if you factor not just by augmentation ideal, but by some character?
So you can do that, but but you in general it doesn't give you the quotient is zero, becomes zero. But so you consider instead module category, not vertex algebra itself. But still there you can argue the same thing. But you can also take any other OPA, non-graded OPA and then you can show that easily that the simplicity follow from this statement. Okay. Now let B be the flag variety of G. Then we have a Springer resolution. And this S sits inside here. So one can take its preimage and this and the it's known I think by Ginzburg the restriction of the Springer resolution to S tilde is a symplectic resolution. And this variety is usually called Srodoi variety. And Dot and Kremenitsa, I'm not sure whether I'm pronouncing the name precisely. Maybe I'm wrong. Gave a localization theorem for finite double algebra using this resolution. So they localized of modulo of a finite double algebra on this Srodoi variety using Richet called asymptotic differential operators. And it's natural to ask whether we have the similar statement for affine double algebra because we have a nice analogy. But it's the localization of a module is difficult. So today I want to do that as a level of algebra. So today my goal is to localize this simple double algebra on the jet scheme of Srodui, infinite jet scheme of a Srodui variety. So we'd like to construct a sheaf of vertex algebra on S tilde infinity, which gives a affine double algebra as a global section. And in doing this, it's important that the Srodui variety can be obtained by a Hamiltonian reduction. This is explained in one of Ginsburg's paper. So I recall the setup of Godwin. So EHF was S2 triple. Then we have the decomposition of G with respect to the action of adjoint action of H. So I take a spin set of H. So and then we have the nilpotent element F gives a symplectic form on this vector space which assign xy to the pairing with F. And we take Lagrangian subspace with respect to this form and define M to be the sum of L and so this is a nilpotent subalgebra of G. And what is important is that the nilpotent element F gives a character on this nilpotent subalgebra. Yes, so this gives a character of this nilpotent subalgebra. then we consider the composition of this Springer resolution with the restriction to M star, which I denote again by mu, and this is the moment map for M action. So where M is a unipotent subgroup as corresponding to M. And chi sits here as a one-point orbit. And it is known by Ginzburg that the, or maybe, okay, so it's known that the M acts freely on the level set mu inverse chi over this moment map, and the fact is that there's an isomorphism. So this we have the action map gives this isomorphism, and also chi is a regular value of V. So we can. So this has a nice property of to perform a Hamiltonian reduction. Then this Srodoi variety can be obtained as a quotient of the level set. And what is important for us is that this Hamiltonian procedure can be done by using BRST cohomology. Which is a result of Constant and Sternberg long time ago. So we consider sheaf corresponding to the BRST cohomology associated with this Hamiltonian reduction. So I don't give a precise definition, but of this differential. But this is really the algebra, differential Lie algebra cohomology, and so this is a Grassmann algebra, and we view this as a super Poisson algebra, and Poisson bracket between these two guys are given by contraction, and the chi is an element here, and which satisfies the square of the adjoint is 0. And the so cost from the recipe of constant Steinberg gives that this sheaf is supported. This is just sorry. This is just this is a super Poisson algebra, and you consider the kernel divided by image by this differential operator. So this sheaf is supported, on the level set, and also its direct image by the projection of the level set to this Rodoi variety is the same as the structure sheaf on the Rodoi variety. And it's easy to generalize this to the chiral, jet scheme setting. So we have this isomorphism gives the isomorphism between infinite jet scheme. So the same thing can be proven by replacing by putting infinity everywhere. So we just have to so we just have to quantize this construction. So basically we replace everything there by the corresponding quantized object. So we have to start with a sheaf of vertex algebra on the Z scheme of cotangent bundle to the flag variety. So but there's already on the flag variety, there's already a sheaf introduced by Marikov, Shetman, and Vane, Torov, and independently by Baileyson. From Greenfield, there's a sheaf called chiral differential operators on the flag variety. So this is a sheaf of vertex algebra, which is roughly speaking, it's locally beta gamma system, which is a natural chiralization of wide algebra. So its associated graded sheaf is isomorphic to the push forward of cotangent bundle to the flag, infinite jet scheme of the cotangent bundle to the flag variety. And its sheaf of Zuse algebra is isomorphic to the usual sheaf of differential operators. So you can think this as an affinization of usual sheaf of differential operators. And it's easy to replace this dv chiral by a sympathetic version in the sense of reshape in the previous talk. So there's a asymptotic chiral differential operators, so the flag variety, which is defined over C H. And we need a sheaf on the infinite jet scheme of cotangent boundary to the flag variety. We claim that we can construct the sheaf we wanted. So sheaf on this. So basically you pull back this sheaf to here and then localize along the fiber. But the vertex algebra is equipped with infinitely many multiplication, which is not associative. So it's not clear whether we can really do this kind of thing. But in this case, we can actually do this because CDO is essentially a free field. So multiplication is so from the fact that it's a free field, the multiplication can be described in terms of bidifferential operators. Just in the case of the contributed deformation quantization. So the Bouchard's relation can be regarded as a relation between these bidifferential operators. So so you can see that this Bouchard relation multiplication is compatible, but vertex algebra structure is compatible with a localization process. Okay, so we define the shift to be just I erased it, but just in the previous, just in the same way. So I take H0 of it was tensor product of Grassmann algebra here. So natural quantization of Grassmann algebra is a Clifford algebra. And there's a natural quantization, natural chiralization or affinization of the Clifford algebra. So we replace Grassmann algebra by this Clifford algebra, which is just a fermionic Fock space. And we take a certain operator again. And if you know the semi-infinite cohomology, it's one can also describe as by the usual notation of the semi-infinite cohomology by in this way. So it's very analog of the algebra cohomology. Okay. So now we can state our main result. So first, this sheaf is supported on the level set, and its direct image on the Z scheme of the Srodoi variety is a quantization of the structure sheaf of the Z scheme of Srodoi variety. And finally, this simple. So if you take a global section of this sheaf, so this is defined over H. So as Rishi explained, we need to take a sister invariant part, then we get isomorphism. So there's a natural action here, and there's a natural sister equivalent structure on this. Okay, this is what we wanted to show. Say.
There are no red side speaker.